In 1931, a young Austrian mathematician published a proof that changed everything, not just mathematics, everything. What Kurt Gödel demonstrated, in 30 pages of notation that shook the foundations of human knowledge, was something that nobody had expected to be true and that everyone wished were false. He proved that within any sufficiently complex logical system, there will always exist true statements that cannot be proven from within that system. Not statements we haven't found a proof for yet. Statements for which no proof can ever exist. Not because the statements are wrong, but because the system that produced them cannot reach far enough to confirm its own truths. Mathematics, the language humanity invented specifically to be complete and certain and absolute, contains truths that mathematics itself can never access. And if you follow the implications of that theorem, all the way to where they actually lead, you arrive at something that has nothing to do with abstract logic puzzles and everything to do with the most important question in the search for extraterrestrial intelligence. Not whether alien minds exist, whether there is any mathematical possibility that we could ever understand one even if we found it. Before 1931, the assumption driving all of modern mathematics was that if you built your logical system carefully enough, made all your axioms rigorous and consistent, then every true statement within that system could in principle be derived from those axioms. Truth and provability were expected to be the same thing. The great mathematician David Hilbert had made this the central program of his career. Formalize everything, prove everything, make mathematics complete. Gödel destroyed that program. What his incompleteness theorems showed is that truth and provability are not the same thing. That any system capable of expressing basic arithmetic will contain statements that are true, but that the system cannot prove. And crucially, this is not a bug that can be fixed by adding more axioms. Adding more axioms just creates a larger system, and that larger system will contain its own unprovable truths at a higher level of complexity. The incompleteness is not a flaw in the architecture. It is a fundamental property of any system complex enough to be mathematically interesting. Now here is where this stops being abstract and becomes deeply personally relevant to any mind trying to understand another mind that operates at a significantly higher level of complexity. A December 2025 paper published on ArXiv, examining what researchers called dual computational horizons, formalized something that Gödel's theorem implied, but that had never been precisely stated in this way. Any reasoning system, including a mind, operates within its own formal framework. It can only reason about things that its own logical structure can represent. And by Gödel's theorem, any such system will contain truths that are true within its domain, but that the system itself cannot reach. What this means for alien intelligence is not abstract at all. If an alien mind operates at a significantly higher level of computational and logical complexity than human intelligence, not things we find difficult, things we cannot even formulate as questions, the gap between our reasoning capacity and theirs would not be like the gap between a child and an adult, where the adult can still explain things in simpler terms, not a difference of degree, a structural barrier built into the mathematics itself. But Gödel's incompleteness is only the first wall. The second one was built by Stephen Wolfram, and it is in some ways even more absolute. Wolfram developed what he calls the principle of computational irreducibility, including any attempt by one mind to model the behavior of another. The principle states this: for most complex computational systems, there is no shortcut. To know what such a system will do, you must run the computation in full, at the same speed, with the same number of steps. No equation, no prediction, no simplified model will tell you the answer in advance. You must watch it happen, step by step, at the same pace it actually occurs. We understand human minds not because we run a complete simulation of every neuron firing in sequence. We understand human minds because we can build simplified models, compressed representations, that capture enough of the essential structure to generate accurate predictions. We know roughly what a person will do in a given situation not because we have simulated every computational process in their brain, but because human minds are similar enough to each other that our models of each other work most of the time. Now imagine a mind whose computational processes are genuinely, radically different from yours. Not faster, not slower, running on different principles, with different structure, at different scales. Wolfram's irreducibility principle says that for such a system, no simplified model will work. To understand it, you would have to run it, and you cannot run it because you do not have access to the substrate it runs on, the processes it uses, or the computational architecture that makes its thoughts what they are. You are not missing data. You are missing the capacity to perform the compression. The gap is mathematical, not informational. The third wall comes from information theory, specifically from the work of Claude Shannon and the concept that later became known as Kolmogorov Complexity. Kolmogorov Complexity is a precise mathematical measure of how much information a given object or process contains. More specifically, it measures the length of the shortest possible description of that object. And here is the mathematical fact that makes this directly relevant to understanding alien minds. The complexity of a mind, the Kolmogorov complexity of its thought processes, sets a hard lower bound on the complexity of any system capable of understanding it. You cannot understand something more complex than you are. A mind with lower Kolmogorov complexity than the thing it is trying to model cannot represent that thing completely. Parts of it will always be compressed away, lost, simplified into something that fits inside the modeler's capacity. And what gets compressed away is not random noise. It is precisely the parts that do not fit the simpler system's framework, the parts that are most alien, the parts that matter most. If an alien intelligence has been developing for 1 billion years, optimizing itself, expanding its own computational architecture in ways we cannot predict or replicate, its Kolmogorov complexity could exceed ours by an amount that makes the word vast meaningless as a descriptor. Not twice as complex. Not 1,000 times as complex. Complex in a way that the ratio itself cannot be expressed in terms human mathematics can handle. And a mind whose complexity exceeds yours by that margin is not something you can understand. It is something you cannot even represent. Attempting to understand it is like trying to store the complete text of every book ever written on a piece of paper with room for a single sentence. Not difficult, physically impossible. The capacity simply does not exist in the container. The fourth wall, and the one that makes the practical implications most concrete, comes from computational complexity theory. The problem known as P versus NP is one of the 7 Millennium Prize problems, the most important unsolved questions in mathematics, each carrying a $1 million prize for a solution. The question is whether every problem, whose solution can be quickly verified by a computer, can also be quickly solved by a computer. It sounds technical. The implications for alien intelligence are anything but. If an alien mind operates at a computational level where problems in the NP class, problems whose solutions we can check but cannot find efficiently, are routinely and rapidly solvable, then the gap between what it can do and what we can do is not a gap we can even describe in terms of speed or memory. It is a gap in the class of problems that are accessible to us at all. We could in principle verify an output from such a mind, confirm that the answer it gave was correct, and still have no access whatsoever to how it arrived at that answer, or what reasoning process produced it. The output would be comprehensible, the intelligence would not be. We would be in the position of someone who can confirm that a piece of music is beautiful without having any access to the mathematical or physical processes that generated it, except that in this case, we could not even hear the music. We could only read the notes. And then there is Turing's halting problem, which completes the picture. Alan Turing proved in 1936 that there is no general algorithm capable of determining, for an arbitrary program, an arbitrary input, whether that program will eventually stop or run forever. The proof was a precursor to Gödel's work and shares its essential character. There is no shortcut. There is no oracle. The only way to know what a sufficiently complex computation will do is to run it. Applied to minds, this means that for any mind complex enough to be genuinely interesting, no other system can predict its behavior without running an equivalent computation. The behavior of a truly alien intelligence is, in the mathematical sense, defined by Turing, undecidable, not just unpredictable in practice, undecidable in principle. No algorithm can tell you what it will do, because the proof that no such algorithm exists is one of the most foundational results in the entire history of computer science. Pull all 4 walls together, and the picture that emerges is not pessimistic in the casual sense of suggesting that understanding alien intelligence will be difficult or take a long time. Gödel says that any reasoning system has truths it cannot reach, and an alien mind far above ours in complexity will be operating in a domain where those unreachable truths are the entire subject matter of its thought. Wolfram says that for computationally complex systems, there is no shortcut to understanding, no simplified model, no compression that preserves enough to be useful. Turing says that the behavior of a sufficiently complex intelligence is formally undecidable, and Shannon says that the information content of such a mind exceeds the capacity of any smaller system to hold. Each of these is a proven mathematical theorem or a formally derived consequence of one. The limit on human understanding of alien intelligence is not a practical obstacle that better instruments or more research time will eventually overcome. It is a structural property of mathematics itself, derived from the same proofs that gave us computers, gave us information theory, gave us the foundations of modern logic. The mathematics that enabled our entire technological civilization contains, embedded in its deepest theorems, a proof of its own limits, and those limits draw a precise boundary around what any mind of our complexity can ever know about a mind that exceeds it. There is one sliver of something that is not quite hope, but is at least not complete closure. Every proof of a limit in mathematics also maps the territory of what lies just inside that limit. Gödel's Incompleteness theorem, by proving what mathematics cannot reach, simultaneously revealed that mathematics is rich enough to talk about its own limitations, which is an extraordinary thing for any system to be able to do. Wolfram's irreducibility principle, by proving that complex systems cannot be compressed, simultaneously revealed that there exist computational processes in the universe that are maximally creative, generating genuine novelty that could not have been predicted by any prior computation. The existence of a ceiling on human understanding of alien intelligence does not prove that the ceiling is close. It does not prove that what lies above it is hostile or indifferent to us. It proves, precisely and rigorously, that it is there. And perhaps the most honest thing that mathematics has to tell us about the search for minds beyond our own is this: The theorems that prove we cannot fully understand them are themselves some of the most beautiful and strange things human intelligence has ever produced, which suggests that even near the edge of what we can know, there is still something remarkable happening.